Welcome. So in the last lecture we have started group action, and in the last result we have proved that a group G acts on a non-empty set X if and only if there exists a homomorphism from G to the permutation group of X. Okay, so let us have more results in this direction. Definition. Let a group G act on a non-empty set X, and let phi from G to Sx be the corresponding homomorphism such that we know the definition phi G of X is equal to G dot X for all G in G and for all X in X. The action is said to be faithful the action is said to be faithful if kernel of the homomorphism phi contains only the identity element of G, where E is the identity in G. Okay, so that means an action is said to be faithful if the corresponding homomorphism is 1 1. Okay, we know that given an action always there exists a corresponding homomorphism, because from action we can convert it to a homomorphism. Fine. Now let us see something. Result. Let a group G act on a non-empty set X. Then the relation on X defined by x1 related to x2 if and only if there exists some g in G such that x2 is equal to the action of G on x1 for all x1, x2 in X is an equivalence relation. This is an equivalence relation. Okay. Let us see. I will not write down the proof. Means I will not write down each and every line of the proof, but I will leave it for you to write it down in your own language. But of course, I will explain that how actually it is an equivalence relation. So let's see. It is reflexive. It is an equivalence relation on what? Equivalence relation on X. So we have to show it is reflexive. How to show? Choose any X from X. So if you choose X in X, I have to show X is related to X. How to show? We always know that identity dot X is equal to X, and identity is an element in G. So it proves X is related to X. Let us consider X and Y to be two elements of capital X such that X is related to Y. This implies there exists some element G in the group G such that Y is equal to G dot X. Okay. Then what happened to G inverse dot Y? G inverse dot Y is G inverse dot Y is G dot X. G dot X. Now this dot is an action. So this is nothing but G inverse G dot X. G inverse G is identity. So identity dot X, that is equal to X. Right? So it proves, therefore, it proves Y is related to X. And so this relation is symmetric. For transitivity, let X related to Y, Y related to Z. See, I am writing informally. I am not writing let X, Y, Z belong to X such that this, but you have to write it. Then it means there exists G1, comma G2 in capital G such that Y equal to G1 dot X and Z equal to G2 dot Y. I want to show that X is related to Z. Therefore, I can write Z is equal to G2 dot Y means G1 dot X. And by using the property of group action, it is G2 G1 dot X. Now your G2 G1 is an element in G. Okay. So thus X is related to Z and therefore the relation is transitive. Okay. So the relation being reflexive, symmetric and transitive is an equivalence relation. Okay. Now let us find a subgroup of a group which acts on a non-empty set. result, let a group G act on a non-empty set capital X and let X belong to X. Then Gx is the set of all G in G such that G dot X is equal to X is a subgroup of G. Okay, this is a subgroup of G. Fine, let us prove. Is it non-empty? Yes, it is non-empty. Why? Since E dot X is equal to X, X is fixed. Therefore, E belongs to Gx. E is identity. So E belongs to Gx. And therefore, Gx is non-empty. Correct? So Gx is a non-empty subset of G. I have to prove that it is a subgroup of G. How to show? Choose elements from Gx. So let G1, G2 belong to Gx. This implies G1 dot X is equal to X and G2 dot X is equal to X. Right? Fine. Then, what can you say about G2 inverse dot X? This is equal to X is G2X. So it is G2 inverse dot G2 dot X equal to, by applying the first property of group action, first condition of group action, G2 inverse G2 dot X, that is equal to identity dot X is equal to X. So if G2 is there in Gx, then G2 inverse is also there in Gx. Therefore, G2 inverse belongs to Gx. I have to prove G1, G2 inverse belongs to Gx. Now, G1, G2 inverse acting on X. This is equal to, by definition of action, G1 acting on G2 inverse acting on X. But G2 inverse belongs to Gx. So G2 inverse dot X is nothing but X. So it is simply G1 dot X. But G1 dot X is nothing but X, because G1 belongs to Gx. So from it we get, therefore, G1, G2 inverse belongs to Gx. Therefore, Gx is a subgroup of G. Right? particular subgroup Gx is called, so as a remark, Gx is called the stabilizer of X, or it is called the isotropy subgroup at X. Okay, either it is called stabilizer or isotropy subgroup at X, because it stabilizes X, that's why. Okay, let us see a property. The property is the index of the stabilizer subgroup is same as the set G dot X. Okay. Okay, what is that? Let me say. What is G dot X? G dot X is this let G act on X and let X belong to X. Then the orbit of X is given by, we call it G dot X, orbit of X under the action. It is the set of all elements of the form G dot X such that G belongs to G. This is called orbit, right? Orbit of X is given by this. Fine. Is orbit a subgroup? What do you say? Is orbit a subgroup? No, that question is not there. Why? Because this is a subset of what? Remember, this is not a part of the definition. Remember always, this is a subset of X. X is not a group. So I am not considering subgroup. Okay. Let us prove a result which relates stabilizer with orbit. Result. Let the group G act on a non-empty set X and let X belong to capital X. Then the index of Gx in G, this is the symbol by which we denote index of Gx in G. You know what is the meaning of index? The number of distinct right or left cosets of Gx in G. So index of Gx in G, this is equal to cardinality of the orbit, the cardinality of G dot x, this set. So this is to be proved. How to prove? We'll show that there exists a biject. How to show that the cardinality? Index is what? Index is one form of cardinality. So how to show the cardinality of two sets are same? If you can produce a bijection from a set to another, then two sets are said to be equivalent and they will have the same cardinality. So basically we have to define a bijection from the set of all, say, left cosets of Gx to G dot x. So proof. Let script L is a set of all left coset. I am not taking right coset because always one x is there, it will create problem. So let us consider left coset. G belong to G, be the let us not write in this way because I require only the distinct left coset. Fine. So let script L be the set of all distinct left cosets of Gx in G. Okay. We define f from script L to G dot x by f of Ggx. Okay. Ggx, we define it to be some element of G dot x. What is the most natural way to define? The most natural way to define is G dot x for every G belong to G. Right? Fine. Okay. Or Ggx in. Okay, that's fine. We have to prove, first of all, let us prove that this is well defined. How to prove? Let G1 Gx, G2 Gx belong to script L. Then G1 Gx is equal to G2 Gx implies G1 inverse G2 belongs to Gx, right? Implies, what is the definition of stabilizer? G1 inverse G2 dot x is equal to x implies by definition this is G1 inverse acting on G2 dot x, this is equal to x. Okay, let us take action. Let us take with action G1 on both sides. This implies G1 acting on G1 inverse acting on G2 acting on x. This is equal to G1 acting on x. This implies G1 inverse acting on G2 acting on x equal to G1 dot x. But this is identity. Identity dot G2 dot x equal to G1 dot x. By definition of action, this is G2 dot x equal to G1 dot x. What is G2 dot x? It is f of G2 Gx, that is equal to f of G1 Gx. Right? So f is well defined. Therefore, f is well defined. Let us prove that f is 1, 1. Let G1 Gx, G2 Gx belong to script L. Then f of G1 Gx is equal to f of G2 Gx. What is the definition? F of G1 Gx? It is G1 dot x, that is equal to G2 dot x. This implies my intention is to prove that G1 Gx and G2 Gx are same. So if G1 dot Gx is G1 dot x equal to G2 dot x, what happened to G1 inverse dot G1 dot x? This has to be equal to G1 inverse dot G2 dot x. Implies this is G1 inverse G1 dot x equal to G1 inverse G2 dot x. Yeah. But what is G1 inverse G1? Identity. Identity dot x equal to G1 inverse dot no dot binary operation. G1 inverse G2 dot x. But E dot x is x. So x equal to G1 inverse G2 dot x. What does it mean? This means G1 inverse G2 belongs to the stabilizer Gx. And if G1 inverse G2 belongs to the stabilizer, then it means by the equality of left coset, G1 Gx, this is equal to G2 Gx. Right? And it proves that f is 1, 1. How to prove that F is onto? You pick any element from the orbit. Let y belong to the orbit of x, g dot x. But every element of the orbit must be of the form g dot x. So this implies there exists some g in G such that y equal to g dot x. Then I want to have an element in the domain. So that element is ggx. This belongs to scriptal, and what is f of ggx? F of ggx equal to, by definition, g dot x, and that is equal to y. Therefore, f is on. Thus, f is a bijection, and so index of gx in G, this is exactly same as the cardinality of scriptal, and that is same as cardinality of the orbit of x. So this proves the result. So this, given any point x in the non-empty set x, if a group G x on x, then the index of the stabilizer of x in G is exactly equal to the cardinality of the orbit of x, right? Okay. Now, suppose gx on x, you can consider it as a definition. Suppose g x on x. The action of g, the action of g on x is said to be transitive. It's said to be transitive if for every xy in x there exists g in G such that y equal to g dot x. Okay, and we say if g x on x transitively, then x is said to be a homogeneous G set. So what does this definition say? This definition says that you have a group which acts on a non-empty set X. Then this action is said to be transitive if you choose any two elements in X then one of them is actually action of some element of G with the other. Are you getting? This definition is actually this, that you have your set X. This is X. This is G. We have action of G on X. This is G. This is X. This action is transitive. If you choose any X and Y, any two elements, then this Y can be achieved by action of some element G with X. G acting on X will give you Y. And similarly, you know, when G acting on X gives us Y, then G inverse acting on Y will give us X. And if this is true for any XY, then we say that the action is transitive. And if G acts on X transitively, then X is called a homogeneous. This is called a homogeneous G set. In general, X is called a G set. If G acts on X, X is called a G set. But the action is transitive. If the action is transitive, then X is called homogeneous G set. Right? Okay. Now let us find out orbits and stabilizer of some point with respect to some action. Then the things will be much clearer for us. Okay, let us see. Okay, so let's see problem. Okay, so suppose let us start with our known examples. So we have seen an action from R cross R2 to R2 given by G dot xy is equal to x plus gy y for all G in R and for all xy in R2. Okay. Okay, nice. Let us check that whether this action is faithful or not. How to check an action is faithful or not? It depends on the nature of the kernel of the corresponding homomorphism. What will be the corresponding homomorphism? The corresponding homomorphism will be pi from the group. What is the group? The group is R plus to the permutation group of R square. So from SR2. That is the group of all bijections from R2 to R2. How do we define it? We define it in this way, that pi of G acting on any element xy on R2 will give me G dot xy. Okay. I have to find out the kernel. What is the kernel? So, if G belongs to kernel of pi, then this will imply pi of G is the identity element in SR2. So, this acting on any element is the same element for every xy in R2. This is the definition. Okay, for every G in R and for every xy in R2. Okay, but according to definition, G dot xy is equal to x comma y, right? Can we say that this means actually G is the identity element? Let us try to find out the meaning of this. By definition, G dot xy is what? Is there x plus gy comma y. So x plus gy comma y is going to be your xy. So this implies gy has to be equal to 0. And if gy is equal to 0, then g has to be 0. Because y need not be 0. Y is any arbitrary. This is 0. This is true for all xy in R2. This is true for all xy in R2. And this is true for all y in R. So this implies g has to be equal to 0. So it means, therefore, the kernel of pi is precisely 0. And therefore, the action is faithful. Okay, the action is faithful. Fix an element and find its stabilizer. So you give me any element in R2, anything you wish. So suppose 1 1. 1 1 is there in R2. I have to find out the stabilizer. So I have to find out G11. What is this? In fact, not G11, it will be R11 because my group is R. So R11, it contains all G in R such that G dot 11 is fixed. Means 11 is fixed. 11 is stabilized by G. This is equal to the set of all G in R such that, what is G dot 11? 1 plus G comma 1 equal to 1 comma 1. So what should be G? It has to be equal to 0. So this set is precisely 0. So stabilizer of 1 1 is singleton 0. Okay. So therefore we have found that the stabilizer of 1 1 in R2 is the trivial subgroup 0. Okay. What will be orbit of 1 1? So orbit of 1 1 equal to R dot 1 1 is the set of all G dot 1 1 such that G belongs to R. What is this? This is equal to the set of all ordered pairs 1 plus G comma 1. G belongs to R. What is this? This is equal to the set of all ordered pairs of the form x comma 1, x belongs to R. Isn't it? Because if you define a function from R to R by fx equal to 1 plus x, it is nothing but a bijection. So this is precisely this, right? What is this? This said, if you draw, orbit is a subset of R2. So if you draw, this is your R2. Okay, if you draw it, your y coordinate is always 1. So it is a straight line which is at a constant distance 1 from x-axis. So this line, this horizontal line is your orbit. So this is orbit of 1, 1. And interestingly, this orbit is actually dependent on the y coordinate. So if I change y coordinate, if I want to find out the orbit of say 10, 1, what will happen to it? It will be 10 plus g comma 1. So again it will be the same thing, this line. But if you change the y coordinate, suppose if you want to find out uh, orbit of say 1 comma 2, then it will be the set of all elements of the form 1 plus twice g comma 2 such that g belongs to R. Okay, and this is also nothing but the set of all ordered pairs of the form x comma 2 x belong to R, because any x can be written in this form. Okay, so what is this? This is the horizontal line at a distance 2 from, this distance is 2 from x-axis. Fine. Okay. Is the action transitive? In order to get transitivity, what to check? If you are given any two elements, say AB and CD, then there must exist some G such that G into AB is equal to CD. That is the procedure. That means you have to show that A plus GB comma B, this has to be equal to CD, right? So the condition is your B and D should be same. If B and D are not same, then it is not possible. That means it is clear from this context, it is clear that this action is not transitive. Why? Because how to show it? To show it precisely, we have one one and 1 2 both belong to R2. R2 is my x. Let G belong to R such that G dot 1 comma 1 is equal to 1 2. This implies 1 plus G comma 1 is equal to 1 2. This is not possible. This is a contradiction straight away. So therefore, for every G, this G is arbitrary. Every G in R, G dot 1 comma 1 is not equal to 1 comma 2. Therefore, the action is not transitive. That means R2 is not a homogeneous R plus set under this action. Okay. So you can try with other actions that we have defined. We have given example So you choose an action and try. Let us try with this simple case. So an example like this. Suppose my x is x equal to 1, 2, 3. Very simple case. And my group is S3. So action is defined from S3 cross X to X. How do I define? We define it as sigma dot X is equal to sigma of X for every sigma in S3 and X in X. In the last lecture, we have proved it is an action. Let us check that whether it is faithful or not. How to check? You have to check the nature of the homomorphism. How the homomorphism will be defined? The homomorphism pi will be defined from S3 to S3, right? How it will be defined? It will be pi of some sigma acting on X. This will be equal to sigma of X because sigma dot X is sigma X for every sigma in S3 and for every X in X. So I need not write it like this. This is same as writing pi of sigma is sigma. So that means this homomorphism is actually the identity function. So this implies your pi is basically the identity function. And so what happened to the kernel? Clearly in that case kernel of pi is identity function. So it should be the identity permutation. So it is faithful. Anyway, it is faithful. Other things you can verify. What about this action? You have a group G. This is also an example. You have a group G. You have a normal subgroup H of G. The action is defined like this. G dot H is equal to G H G inverse for all G in G and H in H. For all H in H. Okay. Is it faithful? To be faithful, you have to define homomorphism from G to its permutation group of H, whose kernel is trivial. So to SH, how it is defined? Pi of G acting on H, it should be equal to G dot H. That means G H G inverse for every G belongs to G, for every H belongs to H. Okay. Okay. Now, what happened? If G is there in the kernel of pi, this implies pi of G is the identity. That means pi G of H is H. This implies pi G. What is pi G of H? Is G H G inverse. This is equal to H. Multiply both sides by G from the right. So you will get GH equal to HG. What does it mean? it means your G belongs to, and this is true for all H. So it means that your G should commute with every element of H. Okay? If your G commutes with every element of H, then your G will be there in the kernel. So necessarily this should be true for right? So what is the meaning? The meaning is your G should belong to normalizer of H. Okay? For every H in H. Okay? G commutes with every element of H. So it is there in the normalizer of H for every H. That's it. So what is this actually? This is called centralizer of H. So this means your G belongs to intersection H belongs to H. It is not necessarily the trivial subgroup. For example, if I choose my G to be an abelian group, if I choose my G to be say R plus, it is abelian. Any subgroup you take, this is your G. You take any subgroup H is equal to say Z plus. Then what happened to the kernel of the homomorphism? You see, whatever real number you choose, it will commute with every integer. So kernel is the whole thing. So in this case, your kernel pi will be the entire R. So you cannot say that this action is faithful. Okay. What about matrix multiplication? Means we defined an action given by matrix multiplication. If you recall, action of GLNR on MNR. We defined an action from GLNR to MNR by A dot M is equal to simply matrix multiplication AM for every A in GLNR and for every M in MNR. Okay. Is it faithful? So what will be the homomorphism? Homomorphism will be defined from GLNR to SMNR. How it will be defined? Pi of a matrix A, this is a permutation now on MNR. It is operating on n by n real matrix. This will give you A dot M, that is simply AM, for every A belongs to GLNR and for every M belongs to MNR. Find out kernel. If A belongs to kernel of pi, then this implies pi A is there, pi A is the identity element. This is equal to what to say? This is the identity in the permutation group S MNR, means the set of the group of all bijections from MNR to MNR. Okay. If this is the identity permutation, then pi A of any matrix M, n by n real matrix M, element of MNR, this has to be equal to M. This implies AM is equal to M. A is in GLNR, so multiply by A inverse on both sides. Okay, no need to multiply this. Well, does this mean that A is the identity matrix? No. So from this, see, it would be identity matrix if this is invertible, but it is not invertible. M is not invertible. So you cannot say that only for identity matrix this is true. There are many matrix M will be there for which AM equal to M. So it doesn't mean that only the identity matrix will do the job, not other matrix. So this action is also not faithful. For example, let us find an example in GL2R. So for the sake of simplicity, let us consider it in GL2R. No. Sorry. My apologies. I made a mistake. You see, this is true. I am saying this is true for all M in MNR. Sorry, I made a mess. If it is true for all M in MNR, it must be true for identity matrix also. This implies AI n by n is equal to identity matrix. But what is AI? AI is A. So A is equal to identity matrix. Yeah, right. Therefore, kernel of the homomorphism pi will be singleton identity. That is the identity element in the GLNR. So it's a trivial subgroup of GLNR, and therefore the action is faithful. Yeah, the action is faithful. Right. So we have seen many examples of faithful actions which are not faithful. We have seen how to find out orbit, how to find out stabilizer, and so on, how to check whether the group action is transitive or not, etc. So I hope that you have understood group action. One important theorem still there, we'll prove it in the next lecture, that is called Burnside's formula. That is one of the cornerstone result in group action. So we'll do it in the next lecture. Thank you. Let me stop.